Real-to-Sim scenes enable generalizable robot data generation and repeatable evaluation. But renderable, editable, reusable scenes remain costly to capture and refine. Is one RGB image enough to recover a simulation RoboSnap environment? Now we can say yes with our RoboSnap. RoboSnap is a layered real-to-sim method that converts a single image into a simulation-ready scene by separating the physics-critical interaction area from the surrounding visual context. Given a single RGB image, RoboSnap first use a vision language model to identify semantic object prompts and then use Sim3 to obtain clean instance masks. For every object in the foreground, the cropped mask is passed to Sim3D for 3D asset generation and an initial camera frame pose. If an articulated object is presented, we further apply a point cloud mask segment model to decompose it into separate movable parts. Next, we register the object assets with the scene point cloud and align the normal of the whole scene with the gravity coordinate. For the background, we segment out the non-interactive region with Sim3 and in-paint the mask using a strong vision language model. The background image is then lifted into a single image 3D world model, producing a fully renderable background layer. We then use set of mask prompting to construct a scene graph, where the graph edge relationships provide spatial constraints for SDF-based geometric refinement and collision hull-based physical refinement. This significantly improves the physical stability of the reconstructed RoboSnap scene. Here we visualize some of the results of our refinement pipeline. RoboSnap's simulation-ready scenes support multiple downstream applications. We can use these scenes for task-specific synthetic data generation for policy training. Besides, the same scenes enable policy evaluation by reporting meaningful correlation between simulated and real-world performance, providing a repeatable evaluation harness for real deployment. Beyond visual alignment, we evaluate simulation readiness of the scenes by loading them into a physics simulation. Compared with Sim3D with foundation pose, and RoboSnap substantially reduces falling, collision and position drift, producing physically reusable scenes. We test whether the recovered scene preserves contact structure by replaying original DROID trajectories. RoboSnap reproduces successful grasp and place events more reliably, indicating accurate object layout and robot-based recovery. Given a task instruction, we instantiate the recovered RoboSnap scene in an LaSoxim-based data engine. The data engine samples grasps, generates 6D of end effector waypoints, and converts them into collision-aware joint space actions. This produces two task-specific data sources, generated demonstrations in the recovered scene, and augmented demonstrations under controlled scene perturbations. RoboSnap-generated data can improve real-world success. Among the three selected ratios, over real, generated and augmented data sources, ratio 2 achieves the best average performance for both Pi 0.5 and Pi 0. We test whether generated data improves robustness under real-world perturbations. And RealSim co-training reduces the average success rate degradation from 13% to 8% across 6 perturbation types. We inference real-only fine-tuned policies in the corresponding RoboSnap scenes in the sim. Simulated success rates show strong agreement with real-world success rates, and trajectory-level analysis of the end effector pose distributions also remain closely matched between simulation and the real world. Third, we introduced DROID-Sim, a companion dataset that converts DROID scenes into reusable simulation environments. For each scene, we extract one representative RGB frame from one of the extrayer cameras and estimate depth, generate masks, reconstruct interaction assets before simulation refinement. This turns a robot dataset into structured real-to-sim scenes. We hope RoboSnap can help turn static digital twins toward reusable infrastructure for robot learning and evaluation. Thanks for listening.